I wasn't really happy with that solution, and I won't be surprised if you weren't either. This video will be a quick exploration of two more approaches to getting random numbers. The 8MB microcontroller is made up of quite a few modules. These videos focus on the CPU, the part that's much the same in all computers. But for this problem, we can use one of the other modules, a timer. Timers run independently of the CPU and are capable of lots of things. We can easily program the 8-bit timer counter 0 to count to 5 again and again automatically. Once that's set up, we just wait for a button press, then grab the counter value. The bad news is that being capable of so much, timers are one of the most difficult sections of the 8MB datasheet. I'm not going to explain it all to you. I don't know it all. But I'll explain what I'm doing here, and you can look at section 19.9 in the datasheet and try to see if what I'm doing makes sense. As you see, shake and roll have become trivial, but the initialization has been turned into a new function. Let's look at it. This sets the LEDs as outputs, like before. This sets the timer to run in CTC mode, clear timer on compare. It'll count up from 0 until it reaches the value in the output compare register, and then start again at 0, just what we want. This tells the counter to use the CPU clock divided by 1024, which means the counter will be incremented nearly 16,000 times per second. And this sets the upper limit to 5 in the output compare register. Once these instructions have been run, you can watch the value in tcount0 as it changes. No need for a program anymore. If you're wondering why we're dividing the CPU clock by 1024, good. Indeed, why not just let it rip at 16 MHz? Then it'll be really random when the button's pressed. That's a question worth exploring because that's what I thought too. But when I tried running it at 16 MHz, I only got even numbers. The thinking is right. If we sample the counter the very moment the button's pressed, it will be random. But that's not what's happening. ArdEx takes about 10 microseconds per instruction. At 16 MHz, that's enough time for 160 increments of the counter. And there are 3 ArdEx instructions between detecting the button press and reading the counter. By the time ArdEx gets the counter value, it's changed hundreds of times. And it would be exactly the same value no matter which of the 6 values was in the counter when the button was pressed. What it really depends on is how the counter clock is synchronized with ArdEx instructions. It's a bit like how filming a propeller can make it look like it's not moving. Ideally, the counter values shouldn't change between when the button's pressed and when the counter's read. 3 ArdEx instructions are about 30 microseconds. Dividing the clock by 1024 means each counter step takes 64 microseconds. This means the counter won't change more than once between pressing the button and reading the counter. In electronics, this problem is related to what's known as the Nyquist frequency. If you want to sample something, samples must be taken at least twice the frequency of the thing being measured. We've done this by slowing down the thing being measured. Don't worry if you don't follow all of that. It just leaves me uneasy about the hardware solution, even though, up front, I thought it'd be spot on. Of course, you're free to experiment with it for yourself. The value in control register B sets the clock speed. 1 is 16 MHz. Details are in section 19.9.2 of the datasheet. I'm much happier with the other approach. It's done by the CPU on its own. We have a lookup table based at RAM address hex F0, where each cell contains the number of the next face of the dice. The shake function updates the dice to the next face, and the roll function doesn't need to do anything. And there can be no slip at all. The moment the button press is detected, the counting stops. I think this approach is pretty tough to beat. Simple, efficient. Just by the way, if the last video had you wondering what I'd have done if memory cells 0 to 5 weren't available, this is an example. You just put it somewhere else and add the base address. This is how arrays are done in C. That really is all on the dice simulator. Just to type what we've done to a well-known programming language, here is the C equivalent of the latest version. I hope you see how it relates to the code we wrote. If there were an ArdEx C compiler, its job would be to convert this C into the ArdEx code. I'll leave you with a couple of challenges. Firstly, a real dice leaves its value visible until the next player picks it up to shake it. See if you can change the program so the value stays visible between rolls. A tougher challenge is to do the dice simulator without the thinker shield and use a 7-segment LED to display a normal digit. The hardware is a little fiddly, and you'll also need a 7th pin, say D5, so you can control all 7 line segments. You could also hook up the decimal point to D6, if you can think of a use for it. For coding, the lookup table will definitely help, but you'll need to work out how to update both port B and port D so the right segments are lit. And bear in mind that for the common anode LED, 0 means on and 1 means off, so things will feel kinda back to front. Has this all been a lot of fuss over nothing? Well, yes, it was far too much effort for a trivial dice simulator. Then again, if it was such an easy problem, why did so many reasonable solutions turn out to be wrong? I'll leave you to think about that. Have fun.